Hey guys, today we're going to be covering section 7.2, which deals with inverse functions. We're going to talk about what they are, some properties of them, how to find an inverse function of an original, and then how to check to see if two functions are inverses. So we're just going to jump right in here. On the screen right now has kind of this key concept from your textbook that says, okay, two relations are inverse relations if and only if one of those functions contains the element a comma b, then the other one has b comma a, and it's flipped around, and it gives an example right here. You know, Q has the points 1 comma 2, 3 comma 4, 5 comma 6. That means S, if they're going to be inverses, S needs to include the points 2 1, 4 3, and 6 5. And so really this makes a lot of sense because the word inverse kind of means, you know, opposite or flipped, or there are probably a lot of connotations you can think of, but that's what inverse functions are. So looking at this, and inverse relations, because it might not be a function and pass that vertical line test. Quick example, just to kind of also show what this looks like graphically. If you read what's on the screen right now, it says the ordered pairs of the relation points -8 comma 3, -8 comma 6, and -3 comma 3 are the coordinates of the vertices of a right triangle. Find the inverse of this relation and determine whether the resulting ordered pairs are also vertices of a right triangle. So here's how I'm going to do this. I'm going to start out by just plotting these points in red. So 1, 2, 3, 4, 5, 6, 7, -8, +3, -8, +4, 5, 6, -3, +3. And we can see this is the original that they told us about. And although my lines are a little wobbly, we can see this is a right triangle. That horizontal line, that vertical line intersect at exactly 90 degrees. Our original is a right triangle. So now let's talk about its inverse. What is the inverse relation here? Well, based on what we saw above, -8 comma 3 in the inverse would become 3 comma -8. We just flip those two coordinates. The signs stay the same, but the x becomes y becomes x. -8, 6 becomes 6 comma -8, and -3, 3 becomes 3 comma -3. So this is how we can find the points of a discrete relation of its inverse, if it's just points. If we put this on the graph, 3 comma -1, 2, 3, 4, 5, 6, 7, 8, 6 comma -8, 3 comma -3, and on this graph, if we see what happened, we see it is in fact another right triangle. So finding the inverse, it doesn't really change the distance between the points or the angle between the points. And this is something that's kind of cool. I'm going to draw a line here on the graph. I'm going to make it purple. That's not a line. Let me try grabbing that shape tool again. So if we drew, there we go, that's a little better. That diagonal line. And you probably recognize that line as y equals x. It's just the identity function, up 1 over 1, up 1 over 1, through the origin. What you'll notice is that to get the inverse, each point was just flipped straight over that identity function. Each point in red was flipped straight across that identity function. Sorry, my keyboard keeps coming up. Reflected over that line y equals x, and it becomes this new shape. So a couple things that I want you to know and you want to grasp from this. If we find the inverse, graphically it's the same as just reflecting over that identity function, over y equals x. And since we're just reflecting, that doesn't change the size, that doesn't change really the shape. I know red to blue got kind of rotated and reflected, but it's still a right triangle. It's still the same size. It was just flipped over that line, y equals x. And last point before I scroll down, this actually makes a lot of sense because what did we do to find those points? We flipped y and x. So the x became the y became the x. That's why it's flipped and reflected over the line, y equals x. So kind of a parallel there, good to know. So one property of inverse functions that you might have picked up on because it's kind of implied by what we looked at above. Let's say that we have f of x equaling x plus 2. That's our original function. And I'm going to tell you right now, in a few minutes we'll learn how to find this inverse function, but I'm going to tell you that f inverse of x equals x minus 2. Now, this is how we write an inverse. F with the little negative 1. It almost looks like an exponent, but f inverse of x is that f to the negative 1 of x. So that's some notation for you. But what was this property I was talking about? Well, just based on this, f of 3, if we're plugging 3 into the f function, that gives us 3 plus 2, so f of 3 equals 5. Well, then that means the property that I'm talking about is, this is saying that 3 comma 5 is a point on this function. What is the corresponding point in the inverse function? The corresponding point should be 5 comma 3. We know that from above. So that means f inverse of 5 needs to equal 3. You can remember that those inputs are the x's into the function. The outputs are the y's. So in red on the left, when we input 3, we got 5, which means in the inverse, if we input 5, we'd better get 3. And you can check it up here and say, okay, 5 minus 2, yes, that does give me 3. So just further driving home the point of how these are related, how their coordinates are just flipped. If we plugged in 20, it gave us an output of 22 for the original. That means if I plug in 22 here, I'd better get an output of 20 to maintain that flipping relationship for inverses, okay? So these problems and ideas we've seen so far are just kind of the concepts, the conceptual, what is an inverse? How do we get an inverse? And for discrete points, for individual ordered pairs, how can we find the corresponding inverse point? But honestly, far more interesting is what if we were working with a function, not individual points, but like an equation? Is there a way to find an equation of that inverse? And the answer is yes. So for this example, I'm going to show you one example, and I'd like you to follow along and on your paper, and then I'm going to have a problem for you to work. But for this example, we are working with that function I just highlighted in yellow, f of x equals 5x plus 10. That is our original function. So to find its inverse, step 1, we're going to replace f of x with y. Why do we do this? Because f of x is kind of clunky to work with in an equation when we're moving around. Those parentheses often get confused for multiplying. So step 1, we're just going to say, you know what? Y equals 5x plus 10. Okay? Now step 2 says switch x and y. And I want you to see, because this is where most of the problems creep in for students, switching x and y is literally that. Just swap their places. Don't take the 5 with it. Don't do anything else. Just put x wherever you saw y, put y wherever you saw x. Okay? And there is a little note on step 2, and I will address that kind of at the end of this example, what I mean by not with word problems when the variables actually mean something. So step 1, replaced f of x with y. Step 2, swap x and y. Again, that's the theme today, swapping x and y. Step 3 is now solve for your new y. So we want to get y alone. We often do that, right? So here I'm gonna subtract 10 on both sides. So x minus 10 is equal to 5y. So y, if we divide everything by 5, and I'll move this down a little bit. x minus 10 over 5 equals y. I'll write it one alternative way as well. We could write that kind of in slope-intercept form. X over 5 minus 10 over 5, we could split that up, equals y, which means 1/5 x minus 2 equals y. So really quickly, just these three are all mathematically accurate. There's nothing wrong with this, but a lot of the time we like seeing things in slope-intercept form, which is why I converted it to the double star down here. And the fourth and final step is just to make sure everyone knows what we're talking about. We want to use that inverse function notation and say, hey, look, we had f of x, but f inverse of x is 1/5 x minus 2. We're just going to replace y with f inverse of x. You'll also notice I flipped it because that's how we usually see it. Again, not strictly necessary, but a nice thing to do to make it look like a comfortable slope-intercept equation for us. So how did we find an inverse function? Well, we took our original. If it had an f of x in there, we just switch it out with a y. And because we're dealing with inverses, we swap the x and y. The x and y then are in different spots, which means y is not alone. So then we solve for y to get y alone. That was step 3. And then at the very end, we'll just pop f inverse of x in for y. So everyone knows it's clear that this was the inverse of f of x. I did want to come back to that point on number 2, talking about switching x and y. Guys, when we have an equation that's just x's and y's, that's pretty generic, and there's nothing wrong with switching x and y. But let me just give you another example, and one that I think you'll recognize. A equals pi r squared. Now, if you remember, that was the equation for area of a circle. We saw that in geometry. Pi times the radius squared is equal to the area. Well, here A and R kind of mean something. A stands for area, R stands for radius, and we don't want to switch them or confuse people about what stands for what. So oftentimes, if it's an equation that stands for something, we will just solve for that other variable. We don't swap them, but we say a divided by pi equals r squared. We could take the square root and take the square root. And so the square root of a over pi equals r. If you were thinking plus or minus r, I'm proud of you, because we always have plus or minus r. But because we know that the radius of a circle is probably positive, I don't even know what a negative radius would mean. We can just include that positive version in this like real world scenario. But I got into this example saying we don't want to switch what a and r represent because they actually stand for something. Just keep them a and r and solve for that other variable. But if it's x's and y's, it's kind of generic. Then just swap x and y and solve for your new y. Okay. That's how we can find inverse functions. So at this point, I would like you to try this problem. Okay, pause this video. I'm going to pause it as well. I'm going to pause the recording. And I want you to try to find the inverse of y equals negative 3x plus 2. So swap the x and y, find your new y, relabel it as f inverse. I'm going to pause the recording, and then when we're both done, we'll both hit unpause, and we can kind of compare our answers, compare our work, make sure we're feeling good about this. All right, by now, I hope that you've had a chance to work this problem out and get as far as you can. You can see my work there. I swapped my x and my y variables. I solved for my new y. And then in the purple box final answer, I did leave that in non-slope intercept form, just x minus 2 over negative 3, which is completely okay. So I did leave it that way just to emphasize that mathematically that is correct. That's totally fine. But on the side in parentheses, you can see I did put that slope intercept form for those of you that felt like looking at it in that form or fashion. It kind of looks a little bit nicer, a little bit more familiar with what we're used to. So hopefully that problem went really well for you. Inverses, I mean, it's a pretty set procedure. Again, just follow those steps, swap the x and y, solve for your new y, and that will be your inverse. Okay, so kind of the last new concept really that we're dealing with inverses and practicing on this video is if we are given two functions, how do we determine if they are in fact inverses? One way you could do already, based on the problem we just did, you could take the first one, find its inverse, and see if it matches the second one. That's one way to determine if two functions are inverses. But the other way actually has to do with function composition from 7.1. If and only if there, if f of g of x just comes out to be x, just one x to the first. If f of g of x, we evaluate it and it's at just x, and g of f of x as well, then those two functions are inverses. They kind of undo each other and we're just left with x in both cases. So problems of this ilk that you might see they'll look something like this. Are these two functions inverses? F of x equals 5x plus 10, g of x equals 1/5 x minus 2. So to check it using function composition, I need to check two things and it has to satisfy both of them. I need to say, well, what is f of, I'll color code the same way I did in 7.1. What is f of g of x? Well, that would be f of 1/5 x minus 2. Because that's what we were told g of x was. We're substituting that in. So let's plug that input into our f function. So our f function was 5 times whatever we're plugging in plus 10. So 5 times 1/5 x minus 2 plus 10. 5 times 1/5 x is just x. 5 times negative 2 is minus 10. And then plus 10 leaves us with just x. The f of g of x kind of canceled them out. And so now we have, yep, f of g of x equals x. However, we're not done. We also want to check g of f of x. So g of f of x would be g of, and then we'll use that definition we had for f of x as our input, 5x plus 10. G of 5x plus 10, so that'll be 1/5 times whatever we're plugging in minus 2 from our g function. 5x plus 10. Distribute 1/5 times 5x is just x, plus 1/5 times 10 is 2, minus 2. G of f of x also works. So final answer, are they inverses? Yes. They are inverses because both f of g of x and g of f of x simplify to just be x. So practicing those skills from 7.1 is kind of what we're doing right now, that function composition. In order for them to be inverses, both of those composition problems have to come out to just be x. So do me a favor, and I'm going to have you, again, pause this video and check to see if these are inverses. Do some function composition, I'll do the same, and then we will check back in when we're both done. All right, and coming back to this problem, hopefully you've had a chance to complete it and you found that these two functions are not inverses. As you can see from my screen, I tried f of g of x. I plugged my g of x function into f. And when I plugged it in, distributed, simplified, I got x minus 15. And since it didn't come out to just be x, I don't even have to check g of f of x because they both have to be true if they're inverses. So if we get one that isn't true, it doesn't just equal x, then we can immediately say, no, these are not inverse functions. So 4 main things we talked about today, kind of just what are inverses, swapping x and y, and on a graph, that means flipping over that identity function. We talked about that property that if x comma y is in the original, y comma x has to be in the inverse. We saw how to find inverse functions, swap that x and y, again, that's the theme today, solve for your new y, that's how you get your inverse function algebraically, and then checking to see if two functions are in fact inverses using function composition, checking f of g of x and g of f of x to see if they cancel out and both just leave x. One final just side note here. How did we tell if something was a function if it passed the vertical line test? If we had a graph, and I'll just draw a parabola here. If we have a graph and anywhere we draw a vertical line, we only hit that graph at most one time, then it is a function. That's how we could tell if something was a function. If you want to know if something's inverse is also a function, well, not the vertical line test, the horizontal line test. As you can see from this example, the inverse of this parabola will not be a function because I'm hitting twice. I'm hitting twice where I drew that horizontal line. So yes, the original parabola is a function, but its inverse would not be a function. Just a quick aside, because very, very occasionally, it's really not a huge deal, but you might see some conceptual questions relating to this. So I thought I'd throw it out there. So guys, you have some practice problems to work on to help you practice finding inverses and checking to see if two functions are inverses and things like that. But let me know if you have questions, if you're working on those practice problems and you're stuck, email me or just circle that one so that when we have class next, you can bring it up during homework questions. But that is all for 7.2. Hoping y'all are doing great, and I will see you next time.